Thanks a lot, Webb, for the invitation. It's my first time here, and it's a beautiful campus. Thank you so much for the invitation. So today I'll be talking about a slightly different energy model-based approach for image reconstruction. So this is somewhat related to all the diffusion talks, but it has some nice properties that will come in handy when we apply this to inverse problems. So let me start with a general setting. I mean, again, it's related to most of the previous talks. So basically, we have an image. We are collecting the undersample measurements in the context of MRI. So we're just assuming that you have a linear operator here. So you get undersample measurements, and we'll be mainly focusing on the image reconstruction task here. So basically, a classical way is to pose this as a maximum a posteriori estimation method. So you have a likelihood and a log prior. And for example, in compressed sensing, you use the standard L1 loss. And there are numerous fast optimization algorithms. And a classical way is, one of those approaches is an alternating minimization scheme where you alternate between a denoising, which is a wavelet shrinkage, and a conjugate gradient layer. And then you kind of iterate through this until convergence. So based on this intuition, the plug-and-play method was introduced. So they basically replaced the denoiser by a CNN-based denoiser, and you have a recursive formulation for inference, and there are nice guarantees for the convergence of the algorithm. So there's a small catch here. So basically, for the convergence of this algorithm, we require the CNN to be a contraction, and this often translates to restricted performance compared to some of these later methods. So the algorithm unrolling based method basically assumes that you have a finite number of iterations, so you unroll it, and then you train this end to end, and this often gives you much better performance than the traditional plug-and-play methods. However, there are some challenges here. So this has low generalization to changes in forward model because you're kind of training this for a specific forward model, and whenever the forward model changes a little bit, you run into generalization issues. And another challenge is the high memory demand. So it's very hard to extend this to 3D or 4D applications. So there are deep equilibrium models which were introduced to overcome this memory demand. So this allows to work with a larger number of iterations, even with larger models. And here again, unfortunately, you have this contraction constraint that restricts performance. So just to summarize some of these methods, I mean, again, I haven't gone through all of those. So you have the non-DL-based map approaches like compressed sensing. They have okay image quality, but they have a lot of nice guarantees like convergence. It works for any forward model because you have a probabilistic representation. You can do sampling, and memory demand was not a constraint. You have guaranteed robustness, and the results were independent of the initialization because you have a convex optimization task. By contrast, when you look at PNP models, I mean, they improve the image quality, and it works for any forward model, but they have a lot of disadvantages. Like, for example, you don't have it's hard to do sampling. You don't have guarantees on robustness, or initialization is a problem. The same thing with end-to-end models. I mean, here you have much better image quality, but then the generalization is a problem. You can't do sampling because these methods are basically learning the map estimate and not really the probability distribution, so it's hard to do sampling. Memory demand is a problem. It's hard to extend this to 3D or 4D problems, and robustness guarantees and all are in general not available. So the outline of the talk, so I'll just get started with energy-based models. So this is I'm not introducing this new. I mean, it has been a very active area of research by all the leaders in the field, including Hinton and LeCun and others. So I'll give a quick introduction on energy-based models, then I'll move on to multi-scale energy models, then I'll look at some constraints on how to make these energy models convex, and then finally I'll talk about how to learn this end-to-end. So the idea is pretty straightforward. So here you have a neural network which outputs a scalar. So the input is an image and the output is a scalar. And the probability is represented as p theta of x is equal to e to the power minus e theta of x divided by z theta. So z theta is basically a normalizing constant. So the intuition is that the scalar is low if you have good images. For example, here, the good images are all here. You have low energy. And then when you're away from it, you get high energy. So now you can take the log of this to get this expression here. So log of p theta of x is this term plus a normalization constant. And a trick that's widely used in diffusion literature is basically take the gradient, and now you get rid of this normalization constant, which is actually can be thought of as a nuisance. So now if you have a CNN, you basically have to take the derivative. I mean, you can use AutoGrad to compute this very efficiently, or you can explicitly compute this. Now, the good thing is that you can train the model in multiple ways. So one thing is this has been an active area of research for several years. So this is a maximum likelihood learning. Okay, so you basically have a lot of data, so which is basically P data. So you take the expectation over all the data of this expression here, and using some tricks, you can rewrite it as shown here. Okay, so you basically have the first term the same. The second term can be computed as shown here. So this is the expectation over all the fake data. So how do you generate the fake data? So this can be done using Langevin sampling. So you basically have the gradients. You can iterate through this very similar to how you do in diffusion. And this gives you fake data. Now, how do you optimize this model? So we have to minimize this cost function with respect to theta. So we simply put the same energy model here, and we try to maximize the difference between the energy on the true data and the energy on the fake data. And so you see that this looks very similar to a GAN. The only difference is that the generator is not a CNN. It's basically Langevin dynamics. Now, the intuition is as shown here. So let's say you have some initial probability distribution. You have some samples here. This is your true data. Now, you start with some noise. You do Langevin sampling. You get to the minima or close to the minima of the probability distribution. Now you try to increase the energy on these samples and pull down the energy on the true samples. And when you iterate, you get an energy that is low for the desired samples and it's high for everything else. So this is a nice approach, but the problem is that you often have to do a lot of iterations here. In diffusion models, it's about out of the thousands, and this results in very slow training. You can use shorter Langevin chain, but this often results in mode collapse and other issues. So there were several methods like contrastive divergence, persistent CD, and replay buffer, and so on and so forth to improve this performance, but it is not it's still an active area of research. So one alternative is to train it in a different way. So here we can use denoising score matching. This is widely used in diffusion models. So you basically just try to learn the gradient. So you basically learn the gradient using denoising score matching. And the result says that we learn a smooth approximation of the log density, and where sigma is the noise that you add in the denoising task. And the main distinction, this is very similar to diffusion models. The only distinction is that the denoiser is a gradient of a potential function. Unlike in diffusion models, you just don't constrain it this way. Now, how do we use this in image recon? So now we have a well-defined potential function or a well-defined posterior. So now we can sample from this, or you can do posterior sampling, or posterior, you can also do maxima posteriori estimations. So the nice thing is that most optimization algorithms are guaranteed to converge to the local minimum without no contraction constraints. Okay, so in PNP algorithms, we are using fixed point convergence, and this often takes a lot of effort, and you need to impose some strong conditions on the network to guarantee convergence. This is not actually needed in our case. And the other thing is that we can impose constraints on the model to enforce some desirable properties such as uniqueness, robustness, and so on. So we tried this. So we took a single scale energy-based model, and we applied this to an image reconstruction task. So this is a four-fold undersample knee data. And we see that the results are really dependent on the initialization. So if you're initializing it with simple A transpose B, you get okay results. But if you initialize with the original, you get pretty nice results. And then if you initialize with random data, you get very different results. And the reason is the convergence to the local minima. So basically, we are just training with a little bit of noise. So the energy is well defined in this region, but away from it, you could have local minima. So depending upon the initialization, you might end with one of these local minimas. So our idea was just motivated by diffusion-like methods and also homotopy continuation that's widely used in non-convex optimization. For example, if you have to trying to minimize the LP norm, you start with L2 and gradually reduce P, and thereby you get good results. So here we are relying on denoising score matching, learning a smooth approximation of log density. So we can use a multi-scale model. So we can use a large sigma where you get a very smooth distribution. And when you do sampling, you converge to the minima, which is well-defined. And then you slowly decrease sigma so that you get a better estimate. So with this trick, so we basically trained energy models at multiple sigmas, and we see that the results are almost identical, independent of the initialization. Whether you initialize with A transpose B or the original or the random, you get pretty close PSNRs and pretty similar errors. So here we are using a sequence of energy. So we train multiple energy models, and we go through that in a sequence. And depending upon the initialization, you see that the cost in log scale decreases as shown here. So this works good, this works well, but the problem is that you need to do a careful schedule optimization to get the best possible convergence, or the fastest results. So to overcome this, we introduced this method called as implicit multiscale method. So the idea is, again, similar to the previous method. So we just now train a single CNN such that it can denoise at multiple noise scales. So it's not a conditional model, it is completely unconditional. So the model learns to denoise at multiple noise scales. And with this, now we can do a simple Langevin sampling as opposed to annealed Langevin, and you can recover good prior samples. And it also introduces some nice properties. So the theoretical result is that if you take an image and feed it to the energy function, it'll tell you how far you are away from the data manifold. So just to showcase this, we took this image and added noise with different variants. And and these are the outputs of the network. So you can see, as you increase the noise standard deviation, the energy value is a quadratic function of how far you are from the image, from the manifold. And you can now consider two independent realization of noise or multiple independent realization of noise and vary the scale, and you see that it's a very well-defined quadratic function of how far you are from the original image. So you get a very well-defined cost, and this means that you get very fast convergence. So we can now apply this to multi-scale, to image recovery as shown here. So you have a single energy that you don't have to work through multiple scales, you just have to work at a single scale. And we can now use all the nice optimization algorithms from compressed sensing. So here we used a majorize minimize algorithm, but you can put your favorite algorithm here. And so here, so the blue function here is, okay, so the green functions here are the MuSE versions. And we have a DPS-like extension, which is the blue one. Okay, so you see that when you use random initialization, the DPS-like extensions often give faster convergence than the one without the DPS methods. But when you use sense initialization, the nice thing is that you can work with any initialization. Now here, it doesn't really matter. Okay, you don't need the DPS-like method, so you can work with a standard method, and it works really well. And the good thing here is that you don't have to start with noise, so you don't have to run a lot of iterations, like thousands of iterations in diffusion models. You get convergence in about 10 iterations if you're initializing it properly. So here are the results. So this is the original image, and these are all the plug-and-play methods, and this is an end-to-end method that's basically model that we trained for that specific undersampling pattern. So we see that the performance is a little bit lacking compared to model, but it is still comparable. And it's better than some of these plug-and-play. Okay, so the PNPs give slightly better PSNR, whereas when you add the contraction constraint, you see that it is much worse. Now we can push the acceleration up, and you can see that here the plug-and-play starts to give you some artifacts. This is because of convergence issues. The contraction constraint restricted that problem, and you get okay results comparable to what you got before. By contrast, this energy model, which is unconstrained, still gives pretty good results. Now, the good thing here is that the end-to-end methods gives improved PSNR, but the good thing here is that you don't need to retrain. I mean, it's a plug-and-play method, so you can apply it to any forward model. So here, the end-to-end model was trained for 2x, but when you infer on 4x, it fails completely, whereas the MuSE method, which is a PNP-based method, it works across all different accelerations. And the nice thing here is that you can also do sampling very similar to diffusion models. So you can also come up with uncertainty maps and do use it for uncertainty quantification if you're interested in that. Okay, so here's some applications. So we applied this to 3D multi-contrast MRI. So this is basically you're applying a 180-degree pulse, and you continuously collect data while the magnetization is recovering. So we are using a 3D Cushball UTE sequence, and we are basically doing reconstruction of 256 cube data. So this is like a large data set. And here, it's very hard to do unrolling, and even with diffusion, it probably takes a long compute time. So here we are reconstructing 4 different contrasts jointly. So we have this energy model trained over 4 different contrasts simultaneously, and it's thereby exploiting the redundancy across contrasts. So with this, the reconstruction time is around 12 minutes for reconstructing 4 256 cube data, which I think is a pretty good start. So here is the 9-minute reconstruction. So this is a reconstruction from 2.5 minutes by using this joint MuSE. And here we used a independent MuSE. So we are not training it jointly for all contrasts. So we are just training independent models for each of those. And so you see that there's a slight improvement in performance by doing this jointly, and especially there's some features, the blood vessels and everything are captured better with this joint MuSE reconstruction. So here is the reconstruction. So this is from a 2.5 minutes MRI scan. So with this, you can get 4 different contrasts, and you can also even do T1 mapping with this approach. Okay, so let me move on. So we were looking at multi-scale energy models. So it can offer some good convergence, but there's no guarantees. Okay, so it is a heuristic method. We have to, and it works well. But now the question is, can we add some additional constraints on the energy model to guarantee global convergence and also robustness? So people have looked at adding convexity constraints to these explicit energy models. And one simple approach is by using ICNN, or the input convex neural network. So basically, it's a neural network flavor where you add some positivity constraints on some of the layers, and that can guarantee that the network is convex. The problem here is that, again, performance. Okay, so when you add constraints on your network, it hurts performance. So our idea is to not introduce these global constraints. So we just enforce local constraints. So we constrain the energy not to be convex everywhere, but just convex around the data manifold. So if your data is lying on a smooth manifold, we restrict the energy to be convex in a tube around it. And this can be done by using a simple Lipschitz constraint. And again, we do that by using a small convexity penalty. So this is a standard MuSE loss. We just have to add a penalty during training to encourage the network to be convex in a small neighborhood. So we can still solve it using the previous methods like the majorize, minimize algorithm, and so on. But the nice thing here is that now we have convergence guarantee, global convergence guarantee. So if the method is initialized within this tube, okay? So for example, if you're initializing it within that tube of radius delta, the algorithm is guaranteed to converge to the unique minimum. So I'll tell you how to initialize it in a second. But we also have robustness guarantees. So if you make some perturbation, so if you make a small input perturbation, the outputs are also guaranteed to be within a range. And this range depends on this M, which is a term that I described in the previous slide, provided this noise satisfies this condition. Okay, so how do you initialize? The initialization is pretty straightforward. So in many cases, you have a simple least square reconstruction, which is very fast to compute. And you can initialize, you can choose this delta so that in the worst case, these least square methods are pretty close, are within that delta. So this approach also brings in some robustness. I mean, it's not only in the guarantees. I mean, we compared the convex and the non-convex methods. And again, this is preliminary results, but it shows that there's some benefit in doing, in adding these constraints. So it can give you improved robustness to perturbations. And here again, just to show that the performance, I mean, it's a little bit smaller than the non-convex MuSE, but it's not significantly worse. So the take-home message is that iMuSE offers several benefits compared to these previous methods. So first of all, it can give you robustness guarantees, can give you convergence guarantees. And because it's a plug-and-play method, it works for any forward model. It gives you comparable image quality to these end-to-end methods. The memory demand, again, it's not a big deal because it's a PNP method, so you don't have to unroll or anything. And the results are independent of the initialization, and it also enables sampling. So there was a little bit of a gap between the MuSE, the plug-and-play methods, and the end-to-end methods. Of course, when you do train everything in an end-to-end fashion, you benefit from the fact that it's seeing all those errors that it's expected to correct. So now the question is, can we train these energy models in an end-to-end fashion? So the motivation is that end-to-end learning offers improved performance, but we know that these unrolling-based methods are associated with high memory demand, and you're basically only approximating the map estimate and not the energy, so this makes sampling a challenge. And then it's also highly sensitive to model mismatch. So now let's look at sampling from the posterior. So you just look at the posterior. So we have an energy here, and we have the data term here. And so let's now look at how to sample from this. Okay, so we can sample from this posterior by using Langevin sampling. And this posterior is usually unimodal, or maybe it has a couple of small modes, and it's much narrower than the prior. So this means that the convergence of this Langevin chain is usually much, much faster than doing prior sampling that is typically done in diffusion models. So now how do we learn this? So we have the maximum likelihood method that I introduced earlier. So here we are switching from the score learning to maximum likelihood learning. So we have this cost function here. Now we generate the samples from the prior by using Langevin sampling, and then we try to do this trick we talked about earlier. So we just do a GAN-like training here. So thanks to it being an energy model, we can either use the previous approach or this approach. So here we are using this approach because this eliminates the need for unrolling. So here we don't need to do unrolling. We can work with arbitrarily large models and apply it to large-scale problems. So here is the deepen method. So the deepen method is the end-to-end trained energy model. And this gives you a really good PSNR, even comparable, better than end-to-end trained methods. And so these are the previous MuSE results. So you can see that you get about a 1.5 dB improvement by using this end-to-end training. And again, this is at an even higher acceleration, so it kind of holds up even at higher accelerations. So now the question is, why do this model work better? Okay, how does the end-to-end training help? So previously, we were just perturbing this by Gaussian noise, but here we are considering a simple, sorry, my bad. Let me just talk about that. Okay, sorry, sorry. Yeah, so previously we were perturbing just by Gaussian noise, but we also now consider a structural perturbation. So let's say we undersample, there are all these LESs. So these are all the LESs we get from a random undersampling, and this is a Gaussian perturbation. Now we consider a combined perturbation, which is a linear combination of the Gaussian perturbation and the structural perturbation. And we see that with a MuSE method, the minimum is often far away from the image. Okay, so when we are doing optimization, it will converge to the minimum, and that minimum is not equal to the original image. With the deepened training, because it's seeing all those LESs during training, it is able to remove the LESs more effectively. And the good thing here is that we saw that end-to-end models were super sensitive to model mismatch. So there's a little bit of mismatch. The method model fails. By contrast, this deepened method, because you're training an energy and not a maxima posteriori estimate, it is relatively robust to model mismatch. So here we trained on a mask that shows like that, and then we train on a totally different mask. We do inference on a totally different mask, and we see that the performance is kind of holding up, whereas an end-to-end trained typical unroll method, or this is basically a deep equilibrium-based method, it actually fails miserably because you're training it for a maxima posteriori estimate. And here again, we can do the sampling. So we can estimate the samples and compute the uncertainty maps. So this is basically the map estimate, the maxima posteriori estimate. We can do get several samples and get the MMSE estimate, and we can also get the uncertainty estimate. So at this sampling rate, we are getting reduced estimate, uncertainty estimate than DPS because we are training everything in an end-to-end fashion. So again, so far I was just talking about image reconstruction. So the same ideas could be applied for other image processing tasks. So this is just a quick snapshot. You could also apply this for end-to-end segmentation. So here we are doing this in a latent space. And so we can do sampling. So the good thing is that even with very small number of sampling steps, like for example 5 or 10, we are still able to get decent segmentations. And the runtime of this method is comparable to a simple NNUnet. So the NNUnet is over here. So you can see that this iterative approach, because you are basically drawing from the image data at each iteration, it's more data consistent and hence offer better performance. So let me summarize. So I introduced this energy models for plug and play and end-to-end image recovery. So in the first part, I introduced a plug and play method. So here we learned the energy, and you can, since it's trained in a plug and play fashion, it can be used for any forward model. This gives guaranteed convergence with most algorithms. And the convergence is fast because you don't have to start with Gaussian noise. You can start with any good initial guess. And provided the initial guess is close to the original solution, you get very fast convergence. And now you can add convex constraints on top of the energy model. So we introduce this local convex constraint, unlike a global convex constraint. And this actually improves robustness while not taking a huge hit in terms of performance. And finally, you can train this in an end-to-end fashion. So the good thing is that you don't need to unroll this. So you can just train it in a very simple fashion. And thus, you can work with larger models and also with larger dimensional data, even 3D data. And this gives you and this gives you more improved performance, but it also reduces the sensitivity to forward model mismatch compared to unrolled methods. And because you're learning in energy, you can sample from it and also quantify uncertainty. So I'll stop here and just want to thank the funding sources, and thanks again for listening.
Talk is open for questions.
Thank you. It's a really great talk. Did I understand correctly that the final trained model is a parameterization of a probability density function through this energy? Is that true?
Yeah, so we are trying to learn the probability distribution. So we are representing the probability distribution. If I go to
so my question was, I guess technically a diffusion model also has an interpretation as a principled probabilistic model of a probability density function. Yeah. But I'm just wondering if you compared to some other methods, like there's one in particular that yours reminds me of, which is deep probabilistic imaging, which they use for the black hole imaging, I think. Mm-hmm. I'm wondering if you've compared to some of those other methods that are directly learning a probabilistic model.
Yeah, that's a great question. Thank you for that. So I totally agree with you that the diffusion models also capture the probability, but in an implicit way. So if you want to calculate the energy, you have to you basically have to run the whole Monte Carlo chain, which takes thousands of iterations, right? So here we are just explicitly modeling it, and that actually helps. I mean, so when you want to do optimization, it's pretty straightforward to use it this way than use it with diffusion.
Yeah, understood.
So yeah, so I'm not sure about the paper you're referring. I haven't seen that, but in general, and I think in the main paper that we publish, we kind of contrasted the diffusion. With diffusion, you need to compute an integral, which is usually done using an Euler sum.
Yes, yes. I'd love to talk to you more about it. Thank you.
Yeah, thank you.
So I had a question only because it stuck in my head since you said it. You had maybe it was an assumption or an observation at one point. You said that the posterior is usually unimodal. I mean, is that a good general assumption for all problems? I mean, it seems to me like you could push things to really poor data, and that may hold less. What are your thoughts on that, and how important is that for if you really push things here?
Yeah. So it really depends on the sampling pattern, right? So if you're pushing things to the limit, like if you have very few samples, I agree it could be multimodal, but definitely it's much significantly simpler than sampling from the prior, right? I mean, so in prior, you have all kind of images. Here, you might have a couple of modes, but it's probably not, it's much, much simpler than a sampling from the prior. So I mean, in our observation, typically when you have some data to work with, some measurements to work with, the number of iterations you need is significantly lower than what you have to do with standard diffusion, because there you're starting with pure noise and you're trying to infer an arbitrary image, right? Whereas here, you could start from a reasonable choice, and then you're just trying to infer from the posterior, which is usually simpler. Again, maybe I pushed it there by saying that it's unimodal, and I agree, if you push things to the limit, yeah, it could be multimodal.
Okay, great. Well, thank you once again.